Let's look at the problem of magnetic monopoles first. This problem stems out of the good theory, which describes the early phases of the universe, and it predicts a series of topological defects, which are magnetic monopoles. We will call MM. These magnetic monopoles are defined by the theory as multiples of the fundamental magnetic charge of Dirac, which is GD. So the magnetic monopoles are defined as a multiple of the magnetic charge of Dirac, GD being the in unit of electrostatic charge. If we have a mass of a magnetic monopole should be defined as such: 4 pi Planck constant times the speed of light divided the electrostatic charge square times m of x being the mass of the Higgs boson. Defined as 10 to the minus 1 mass of good, because the Higgs boson is the mediator of the good interaction. So this gives us that the mass of the magnetic monopole should be around 10 to the 3 of the mass of the Higgs boson, which is around 10 to the 16 giga electron volt, which equals 10 to the minus 8 grams. Equivalently, they should have a dimension, so radius of the magnetic monopole, of around Planck constant divided the mass of the Higgs boson times the speed of light. And we should have a numerical density of these magnetic monopoles in the space, which depend of a characteristic length, which is this epsilon minus 3 mm, which is the characteristic length of correlation of Higgs field. So we know, and this is just an obvious consequence of what we know theoretically, and the definition of cosmological horizon is that this length must be smaller than the cosmological horizon. So we cannot have the distance between two magnetic monopoles, so the length of the interaction uh, between them, to be bigger than the cosmological horizon, because we know that the cosmological horizon defines a space in which there is causality between events. And so we have that this value must be bigger than the volume of the cosmological horizon. So we can write the horizon radius as 2 times the speed of light times the good interaction time. And so this writes an mm at the good time is bigger than 2ct good minus to the minus 3, which equals 10 to the minus 10, and gamma t good, where n gamma is the numerical density of photons. So this quantity, the numerical density of magnetic monopoles, which is related to the numerical density of photons at that time, the good time, is actually what we would consider to be the numerical density of magnetic monopoles at modern time, at today time, t0. And that is because this kind of interaction do not vary in time. So throughout the evolution of the universe, this number density wouldn't be modified. And so we would find that at the present time, still the density, numerical density of magnetic monopoles would be around 10 to the minus 10. But if you look at the numerical density of baryons, so baryonic matter, it also has an order of magnitude which is kind of the same. And so it means that if this is all correct, and mathematically it is correct, we should have a density of magnetic monopoles that is equal, almost equal to the density of baryonic matter. And that cannot be physically possible with the observed universe because of such a high density, because it's a high density of magnetic monopoles would lead to a collapse of the universe, because a monopole is charged in a specific way, and so many magnetic monopoles in a such high density would lead to a complete collapse of the universe, and it wouldn't take the time that we observe. It would be a few seconds just after the Big Bang, very a fraction of seconds, with such number density of magnetic monopoles. So this cannot be. And we will see that inflation, so a period of accelerated expansion just after the Big Bang is something that can dilute the numerical density of magnetic monopoles in order to not have the universe collapse just seconds after the Big Bang.